Okay, I'll be picking up here 8.3, starting on number 19. All right. So let's see what we've got here. Sum n equals 2 to infinity of 1 over n natural log n. All right, well, I see something right away. I see that if this were an integral, the derivative of natural log of n is 1 over n, which I have right here. So I'm already starting to think integral test. I could do comparison test. The question would be, what do I want to compare that to? Let me go with the integral test. I think that's where we'll have the most success here. Not to say that a comparison test won't work. So what do I need? First of all, I need to convert the series, right, and the sequence in here to a function of x. And then I need to check some conditions first before I can apply the test. So is f continuous on the interval 1 and infinity? Well, actually, I only need to look at 2. And let's see, I just got to make sure there's nothing. Oh, I forgot to put that as an x. Got to make sure that I plug in 2, I don't get division by 0 here. So 0 would give me division by 0. It's not in here. And then natural log of 1 is 0. So, well, 1's not in here, so I should be okay. The next thing I need is to make sure that n is positive. That f is positive. So is f positive on to infinity? Well, if I'm plugging in positive numbers, that's going to be positive. Natural log, well, we do get negatives with natural log. Remember, the natural log function looks like this. But this is at 1. And so after I get past 1, the natural log function is positive. So I know that this is also positive. And then now I need to show that it's decreasing. So f decreasing. It's positive, it's continuous. Eventually, right? So let me take the derivative there. F prime of x equals, now there's several ways you could do this. I guess I'll just use quotient rule. The derivative of the top is 0 times the bottom minus the derivative of the bottom, that's a product rule. Derivative of x is 1 times natural log x plus derivative of natural log of x is 1 over x times x. So that's my product rule. And then times the top all over the bottom squared. And let me figure out what that is. So f prime of x is equal to, let's see, this goes away. I get negative to distribute through, negative natural log x. 1 over x times x is going to give me 1, but I distribute a negative through, so negative 1. Over x natural log x squared. Now, the bottom is always positive. In the numerator, well, natural log of x, I know that this piece right here is always positive as long as I'm past 2, or past 1, in fact, but I'm starting at 2. So that's always positive, and then make it negative. So negative number minus 1 is still negative. So I have a negative over a positive. That checks out. That's negative. So my function is decreasing. Now, once I've satisfied all the conditions for the integral test, I need to make sure I can integrate this. So let's try this integral. I'm going to do the integral from 2 to infinity of 1 over x natural log x dx, which is the same as the integral from 2 to infinity Let me write it this way. 1 over natural log x times 1 over x dx. I'll make a u substitution here. U is natural log x. Du is 1 over x dx. So I have du right here. This is 1 over u. So this integral becomes, actually, you know what? Let me do the indefinite integral first because I'm going to switch it to u. So this integral becomes integral 1 over u. This is du. And the antiderivative of 1 over u du is natural log of the absolute value of u, plus a constant. But what was u? U was natural log of x. Huh, interesting. So here's what we've got. We've got integral 2 to infinity of 1 over x natural log x dx equals the natural log of x evaluated from 2 to infinity. Now I should be using a limit here. So let me go ahead and do that limit now. So I have that this equals limit t goes to infinity of natural log of x evaluated 2 to t, and then limit t goes to infinity, and then when I plug in t, I get natural log of t, minus when I plug in 2, I get natural log of 2. All right, and now let t go to infinity. As t goes to infinity, we get natural log of infinity, which is infinity, natural log of infinity again, which is infinity. So this is becoming infinite minus, this is a number, it doesn't matter. So this thing is diverging. So therefore, by integral test, our series does whatever the integral did. So it diverges. And that's it. All right, let's take a look at number 20. Okay, for 20, sum n equals 1 to infinity of n squared minus 1 over 3n to the 4th plus 1. Let's see if I can get a better marker. That's a good one right here. All right, so let me see here. If n gets really big, this looks like I can compare it to sum n equals 1 to infinity. The top's acting like n squared. The bottom's acting like, I'll put 3n to the 4th. I could just put n to the 4th, but I'm going to put 3n to the 4th, which is really just sum n equals 1 to infinity of 1 over 3n squared. This is a p-series with p being 2, which is greater than 1, which means it converges. Remember, the 3 here could come out as a 1/3 and it would still converge. So I've got a convergent series that I think this one compares to. So what is it that I want to show if I'm comparing my series to a convergent series? Well, I want to show that my sequence, a sub n, always stays smaller than or equal to b sub n, where b sub n is this one. I'll also check real quick if n is 1 This is 0. If n is 2, that's a positive over a positive. So this is greater than or equal to 0. It's, you know, definitely at 1, it's 0, but past that, it's going to be positive. And then over here, this is always greater than 0. So we're going to be able to use the test. So let me see if I can show that this is true. Remember, if all of these are adding up and they're converging to a number, then if my numbers here are smaller than these or equal, then mine should add up to be a number also. So I want to show that n squared minus 1 over 3n to the 4th plus 1 is less than or equal to 1 over 3n squared. And then I do some, you know, algebra here. Let me see, if I multiply both sides by 3n squared, it goes away over here. It becomes 3n to the 4th minus 3n squared, less than or equal to, this times 1, 3n to the 4th plus 1. So let's see, if I subtract 3n squared, or 3n to the 4th on both sides, it goes away. And what I'm left with is negative 3n squared is less than or equal to 1. And this should always be true. You could just switch them. You can move, you know, add this to this side. You could get, or not even switch them, just move this to the other side. You get 0 on the left side. On the right side, you get 3n squared plus 1. And this is always true. As long as n is a positive integer, we're good to go. So we've shown that it compares, so we're ready to draw our conclusion. Therefore, our sum, n squared minus 1 over 3n to the 4th plus 1 converges by comparison test. So I wasn't thinking integral test here, because if I were to imagine this being an integral, that's not something that I'd really want to go after. It's, I'm sure we could integrate it, but it would just be a lot uglier than this was. All right, let's look at 21. Sum n equals 1 to infinity. Cosine squared n over n squared plus 1. All right, so that cosine squared n on top starts to make me think of something like a squeeze theorem. Oh, shoot. Am I not recording? Where's my audio? I hope I've got audio. Yes, I do. Okay. That was a little bit scary. I noticed that my cosine squared n, I know that has always got to be between 1 and 0, right? Cosine is always between -1 and 1, but if you square it, it's got to be positive or it could be 0. So I know that. So the top is really like, I mean, you could look at it when you're trying to compare it to something. Maybe this is something like a 1 over n squared plus 1. Yeah, it's worth a shot, right? I mean, try and compare it to that. I don't want to integrate that. I really don't want to integrate that because I've got cosines mixed with a polynomial. That would probably be pretty ugly. So let me try and compare it. So let's see what my comparison series would be. Maybe sum n equals 1 to infinity. Maybe 1 over n squared plus 1. So what is this? You'd have to know what this is. Well, if that wasn't there, that's a p series. And that would be p being 2, and that would converge. Adding 1 to the bottom is not going to change the convergence. You could check this for yourself. that we could go and do a comparison of this to this and figure out from a comparison test that this converged and that converged. You could also do an integral test on that to show that that converged. But because we're adding just a constant onto this down here, it doesn't have an n here, we'll be happy to just say, hey, look, that's basically a p-series. It's a p-series with p being 2. So p-series, p is 2, greater than 1, converges. So I'm going to be comparing the sequences to each other now and hoping to get an inequality to work out here. This is going to be my b sub n. It's greater than 0. This is my a sub n, and that's also greater than 0. It could also be equal to 0, depending on whether or not that cosine turns out to be 0 on top. But they're both positive, or they're both non-negative, so we should be okay here. I want to show, since that one converges, that my a sub n's stay less than or equal to my b sub n's. So I want to show that cosine squared n over n squared plus 1 is less than or equal to this one, which is 1 over n squared plus 1. And if I multiply both sides by n squared plus 1, I get cosine squared n is less than or equal to 1. We already knew that that was true, right? We talked about that earlier. This is always greater than or equal to 0. So this should always be true. So I'm good. So that's going to converge. Therefore, series n equals 1 to infinity, cosine squared n over n squared plus 1 converges by comparison test. Now, I do want to show this. I mean, I'm done here, but I do want to take a moment to take a look at this. Let's show that this one converges. I really want to kind of convince you that this one converges. Even though we say it's a p-series, that plus 1 does have an effect on things, but I want to convince you that's not going to matter. Maybe I can do it in a general way. No, that might be a little bit more than I want to do here. Let's try and take that as its own problem. Okay, and what I'm going to do is I'm going to set up a function. I'm going to do integral test. I'm going to do this. This is obviously continuous. It's positive. And is it decreasing? Well, if I take the derivative of this, let's see what we get. I would actually do quotient rule, so derivative of the top, which is 0 times the bottom won't matter, minus derivative of the bottom times the top over the bottom squared. This is definitely a negative number on top. As long as x is positive, this is a negative number. The bottom is always positive. So yeah, that checks out. This means f will be decreasing. And now I just need to be able to integrate it. So I've got everything I need. So I need to do the integral from 1 to infinity of 1 over x squared plus 1 dx, which is going to be arctangent of x. That look familiar? 1 to infinity. Now I need to set up a limit, but because I'm just real quick sketching this out for you, let's just think about this. If I'm going to plug in infinity for this, the arctangent of infinity, remember we've done this a lot, is pi over 2. And then minus what we get when we plug in 1, so tangent inverse of 1 is pi over 4. But the most important thing is that this is a number, and that converges. So this integral converges means that converges. So it worked. Okay? So I guess the moral of the story is this, and maybe I'll mention this in lecture, I don't know if I will for sure, but if you have something like this, sum n equals 1 to infinity of 1 over n to the p plus some constant, that this, if p is less than or equal to 1, it will diverge. If p is greater than 1, it will converge. So having a constant out here, like that's a p series, having a constant out there has no effect on anything. It's still going to hold true. Hey, you're welcome to come in, but you got to give me half an hour.
No, I just want to ask.
Oh, sure.
Am I able to, do you think I'll be able to take the test right now? Or is there going to be telescopic questions on the exam? Because on the homework there's only one.
It covers all through series. I'm pretty sure there's telescopic on there.
Yeah, because on the homework there's only one, and I was able to get that.
If you could do the one on the homework, you should be okay.
Okay.
Yeah.
Yeah, because I want to knock it out.
Yeah.
Pretty complicated.
Yeah, if you feel good about it. As long as, I'm trying to think, I pulled all the exam problems from the homeworks.
Oh, okay.
So if you were okay on the homework, you should be okay on the test.
Okay.
Yeah. It's not due till what, Saturday?
Yeah.
Yeah, so okay, yeah. I decided I'm not going to try and push anything past 8.2 on that test. So you should.
Well, Saturday I was able to do all of 8.2, so.
Okay, good.
The homework, so.
Okay.
Yeah.
Yeah.
I actually like this.
That's cool. Good, good, good.
See you later.
Okay, I'll be here. I'll be around if you need me. Okay. All right, let's move on. 22. 22. Sum n equals 1 to infinity of 4 plus 3 to the n over 2 to the n. Well, my instinct here is to try and split this up into 2 and make it like 4 over 2 to the n plus sum n equals 1 to infinity of 3 over 2 to the n. So these were both to the n, so I put them together. And then over here, I could take this 4 out, make that a 1. Here's the problem I'm going to run into, though, is that this right here, okay, if I look at this right here, well, let me rewrite it. 1/2 to the n. That's a geometric series. I need to tweak it a little bit to get an n minus 1 here, but that's a geometric series. The r here is 1/2. That should converge, so that's okay. This one, though, is geometric, and the r here would be 3 over 2, which is bigger than 1. That would diverge. So I'm not really allowed to split it up unless they both converge. So I need to really come back here and just make sure that this over here that I can't tell it diverges from just this. So let's see here. Let's do a comparison. Let's compare it to this. Let's compare it to, I hope you understand, if I can only split up a series into 2 separate series if they both converge. If one of them diverges, you're not allowed to split them up, all right? So I'm going to compare it to this, because I think this thing diverges. I'm going to compare it to this, because that's really, this is this with the 4 taken away. And we know that with this 4 here, it makes my numerator a little bit bigger than the numerators over there. And so all of these should be bigger than those, and I already know that diverges. So perhaps that's enough. So I'm comparing to this. This is a geometric series. I do not need to find out what its sum is, okay? I don't need to go through and tweak it. I just need to look and notice that this is my r. And if it's a geometric series, the absolute value of r here is equal to 3/2. That's bigger than 1. This is going to diverge. So now what I'm going to do is I'm going to be comparing this thing, which is my b sub n, to this thing, which is my a sub n. And remember what I'm trying to show now with the comparison test, since this one diverges, I need all of these to be a little bit bigger than those. So I need my a sub n's to be bigger than or equal to my b sub n's. So let's check it. Is 4 plus 3 to the n over 2 to the n greater than or equal to this, which I'll write as 3 to the n over 2 to the n. So I multiply both sides by 2 to the n, and they go away. And I'm left with 4 plus 3 to the n greater than or equal to 3 to the n. Subtract 3 to the n on both sides, I get 4 is greater than or equal to 0. That checks, so this holds. Therefore, the series n equals 1 to infinity of 4 plus 3 to the n over 2 to the n diverges by comparison test. Sum n equals 1 to infinity. Oh, okay. N minus 1 over n 4 to the n. There we go. Interesting. I'm not thinking integral test here, because if I do integral test, I don't want to integrate that inside. That looks too ugly. Well, comparison, what do we want to compare it to? If n gets really big, the top acts like n, the bottom acts like n. So let's just think about that. If we look at n getting really big, the top really behaves like n. This bottom here behaves like n 4 to the n, and these n's would cancel, which means this really looks like it might be behaving like 1 over 4 to the n, which is really just 1/4 to the n, which is geometric. It's a geometric series with r being 1/4, which is less than 1, which means this converges. So I'm thinking that this converges, and I'm going to compare it to this convergent series. And this is the one I'm going to be looking at right here. This is my b sub n. This is my a sub n. This is greater than or equal to 0. This one is actually always greater than 0. So what I want to show, think through this again, if this one converges, then I want all of these to be smaller than these. That way they add up to be something less than whatever that is. So I'm going to try my inequality a sub n less than or equal to b sub n. So I want n minus 1 to be over n 4 to the n to be less than or equal to 1 over 4 to the n. Let's multiply both sides by 4 to the n. Like that. Let's multiply both sides by n. And we get n minus 1 less than or equal to n. Subtract n on both sides. We get negative 1 is less than or equal to 0. That's true. So this holds. Therefore, my conclusion is that my original series converges by comparison test. So therefore, converges by comparison test. You may get tired of writing this over and over, but that's what I'm looking for. You need to draw it all, write it all out, explain every step, and then draw your conclusion at the end. Okay. Sum n equals 1 to infinity. One over cube root of n cubed plus 1. Is that right? Oh, square root. Square root. All right. This one looks a little troublesome. So I'm not thinking integral test again because I don't really want to integrate that. Maybe if that were n squared I would, but it's not, it's n cubed. So if n gets really big, what does this behave like? The 1 really won't matter anymore, will it? So this really looks like it's going to behave like 1 over 1 over the square root of n cubed, which is really just 1 over n to the 3 halves. And that's a p-series. P is 3 halves, which is greater than 1, which means this converges. And so I'm going to be wanting to compare, well, either one of these. B sub n, it's greater than 0, obviously. I want to compare it to this, which is my a sub n, which is again greater than 0. And what I want, since that one converges, for this one to be smaller than that one. So I want to show a sub n is less than or equal to b sub n. So I want to show that 1 over the square root of n cubed plus 1 is less than or equal to, I'm going to use the top one up here, 1 over the square root of n cubed. All right. Let me just cross multiply and get this. I don't like using the term cross multiply. What I'm really doing is clearing fractions on both sides, but students seem to like that when I say that, so I'll stick with that. All right, so this hopefully is obvious to you. This number is smaller than this number because you're adding 1, so everything else is identical. You could square both sides and get this, and then subtract n cubed. Check, it's good. So let's draw our conclusion now. So therefore, my original series converges by comparison test. I'm thinking that some of these are going to get more challenging. Let's see. 25. Let's see how I'm doing on time here. I'm good. 25. Sum n equals 1 to infinity. One plus 4 to the n over 1 plus 3 to the n. Don't want to integrate that. I want to compare. And I'm thinking again, as n gets big, those 1s really don't matter. I'm thinking that this acts a lot like 4 to the n over 3 to the n, which is really 4/3 to the n, which is geometric. I've got r being 4/3, which is bigger than 1, so it's going to diverge. So I just need to show that these guys here my a sub n's, which are positive, are always bigger than my b sub n's, which are also positive. So let's see if I can show that inequality is true. I want to show that my a sub n's are always bigger than or equal to my b sub n's, or eventually this happens. So 1 plus 4 to the n over 1 plus 3 to the n is greater than or equal to 4 to the n over 3 to the n. All right, let's multiply both sides, like clear out the fractions. So I multiply 3 to the n over here. I get 3 to the n times 1 plus 4 to the n, greater than or equal to, over here I get 4 to the n times this over here, so 1 plus 3 to the n. We haven't seen anything like that before. That's all right, we'll just distribute. So here to here, here to here. So you get 3 to the n plus 3 to the n times 4 to the n is greater than this side, 4 to the n plus, again, distribute through 4 to the n times 3 to the n. And these are exactly the same. These cancel, and then you get 3 to the n is greater than or equal to 4 to the n. And that is not true. 4 to the n is bigger than 3 to the n, as long as n is 1 or 2 or 3 or 4, which it is in this case. So that is not working, right? That's not working. So let me see if there's something else I can compare this to. So this is a good example of one that didn't work out. I've been waiting for one of these. So let me go back here. What was the problem that I had? The problem that I had was that when I did this over here, right? When I did this multiplication here to here, this 3 to the n, then this, I need this side to be bigger than the other side. So maybe instead of using 3 to the n, I use 4 to the n down here to make this side bigger. And so this is such a great problem to show you something. I'm going to continue. I see how I'm going to do it, but I'm going to continue with this logic of trying to make this side bigger. So let's see. Instead of comparing it to 4 to the n over 3 to the n, let me compare it to 4 to the n over 4 to the n. Well, wait a minute. That's just 1, isn't it? Isn't that just 1? So I'm comparing this thing. This is my new b sub n. I want to show that my a sub n is bigger than my b sub n. So I want to show that this is just bigger than 1. And so when I do my clearing of fractions, I get this is bigger than this, and get rid of the 1's, and now it works. Now the question though is, what does this series do? Well, this is just 1 plus 1 plus 1 plus 1 plus 1 forever. This obviously diverges. And so this inequality was true. This held, so it diverges too. So I've shown you how you can do it, but let me take a step way back to the beginning of the problem, because what happens is you get so embedded in what you're trying to do that you lose sight of something very simple in the very beginning of the problem, which is the very first test on our list of tests, the nth term test. The nth term test says take the limit as n goes to infinity of the sequence you have here. 1 plus 4 to the n over 1 plus 3 to the n, and figure out what happens. Now, we would have to use L'Hopital's rule, because this goes into infinity over infinity. We get derivative of the top, which is 4 to the n times natural log 4. Now, I'm keeping everything in terms of n. We know that when we use L'Hopital, we have to switch it to x, but I think we can do this without going crazy, right? Without losing our minds. Okay, now once we do that, notice that this is the same as limit n goes to infinity of 4 over 3 to the n times natural log 4 over natural log 3. This is just a number out here. But this is a number right here, it's bigger than 1. And we're raising it to a power that's getting bigger, so that thing should blow up. And that means that this thing goes to infinity. And so this limit is infinite. And the end term test says that if the limit as n goes to infinity of your sequence is not 0, it diverges. And that's not 0. So this thing diverges. I could have been able to determine that from the very beginning of the problem by just doing the end term test. Now I still got it with the comparison test, but I think that would have been a lot easier. All right, so I would do that, and then I would say, you know, converges by the end, diverges by the end term test. That was good. I wasn't ready for that one. It got me. So I wasted some time on that. 26, sum n equals 1 to infinity. This one was going to be easy. 1 over 2n plus 3. The only reason this one is easy is because I've told you what you can do in this case. If you have a constant over a linear expression, then this is a harmonic series. So this is, we're going to say this is harmonic, and so it diverges. Right? I would recommend that you go through and try and show this is true. Like I would do this and maybe compare it to this and see if it works, because that's harmonic, especially if you pull the 2 out. Or you could do integral test on this also. Just good practice. 27. Sum n equals 1 to infinity. I always have to check, because sometimes these don't start at 1, so you have to be a little careful. 2 plus negative 1 to the n over n root n. All right, we have an alternating series here. We haven't seen this before. It's the first time since we've started working with series that we saw a negative 1 up there. So let's try and consider what's happening here. This is always going to oscillate back and forth between negative 1 and 1. So the top is either going to be 2 plus 1, or it could be 2 minus 1. In this case it's 3, in this case it's 1. So the top is really just switching back and forth between 3 and 1, 3 and 1, 3 and 1 as we move out. And then the bottom is blowing up, it's going to infinity. So definitely don't want to integrate that, because I can never integrate a negative 1 to the n anyway. So I'm going to try and compare it to something. So I'm thinking like worst case scenario here is that we've got something like this. Like a 3 on top and then n root n. And then that's really just, I can pull the 3 out. 1 over, and then this is really n to the 3 halves. And that's a p series. P is 3 halves, which is bigger than 1. Well, bigger than 1. Which means it converges. Which means I'm going to need to somehow show that this guy right here, which is positive, since this converges, I need to show this, which is also positive. I need to show that this one stays smaller than that one. That a sub n somehow is always less than or equal to b sub n. So I need to show that 2 plus negative 1 to the n is over n root n is less than or equal to 3 over n root n. Multiply both sides by n root n, they're gone. And then we'll have 2 plus negative 1 to the n less than or equal to 3. Let's subtract 2 on both sides. Negative 1 to the n less than or equal to 1. You agree with that? This is either a 1 or a negative 1. If it's negative 1, it's definitely less than or equal to 1. If it's 1, it's definitely less than or equal to 1. So I'm good to go. So since I found a convergent series to compare it to, and the inequality held that I wanted, my conclusion is therefore the series n equals 1 to infinity of 2 plus negative 1 to the n over n root n converges by comparison. I'm getting a little lazy now. I would like to show you though what would have happened if you would have said, you know what, let me compare it to this. Let me do this in a different color. What if you had not put that 3 there? You would have done 1. Then this would still be a p-series. It would still converge. But this over here would change. This would now be a 1. And so when you got to this, you would say 2 plus negative 1 to the n is less than or equal to 1. And when you subtract 2 on both sides, you get negative 1 to the n is less than or equal to negative 1. And this is not going to hold all the time. Because if n is 2, this is 1, and 1 is not less than or equal to negative 1. So you may have thought, well, that 3 is not that important, but it is absolutely important in order for this inequality to hold. And so why did I use the 3 instead of 1? Well, remember, we said the top here, you know, could have been a 3 or it could have been a 1. I went with the bigger one because I was trying to look at like worst case scenario, the biggest this could actually ever be. Okay, I hope that makes sense. If the 3 wouldn't have worked, I probably would have tried the 1 after that to try and somehow get that inequality to work my way. Not saying it would have worked, but. All right, I'm getting close here to the end of this assignment. Wow. All right, 28, sum n equals 0 to infinity. One plus sine n over 10 to the n. That sign in there is making me think that, again, kind of like worst case scenario, what if the biggest this could ever be would be 1. So the top, the biggest it could ever be would be 1 plus 1, which would be 2, and the smallest it could ever be would be 0, right? If sine is negative 1, sine of n is negative 1, this would be 0. So worst case scenario, I get 0 on top or 2 on top. So why don't we compare it to a 2 on top, like that. And then pull the 2 out, or you know what, let's not pull the 2 out. Let's put the 2 in front and then do 1/10 to the n like that. And this is geometric. The r we have is 1/10, less than 1, converges. I hope that I've made the point that you do not have to go and rewrite this as n minus 1 and all that, because it doesn't really matter. We just want to recognize it's geometric. Although, because it starts at 0, that would have been fine. We'll just leave that as is. Okay, convergent. So it converges. What I need to do is compare this b sub n, which is greater than 0, to this right here, which is actually greater than or equal to 0, could actually be 0. So I have to include the equal there. And since that converges, I want these to be smaller than those, or equal to them. So I want to show that my a sub n's are less than or equal to my b sub n's. So I want to show that 1 plus sine n over 10 to the n is less than or equal to 2 over 10 to the n. I can multiply both sides by 10 to the n, which leaves me with this. Subtract 1 on both sides, and I get sine n less than or equal to 1. That's always true. And so this works. So now I'm going to get real lazy because I'm trying to get this video in under an hour. Therefore, this series right here converges by comparison test. That was 28. See what 29 looks like. Well, is n, let me do the nth term real quick to see what happens. Nth term, test. What is the limit as n goes to infinity of sine 1 over n? Well, as n goes to infinity, 1 over infinity goes to 0, sine of 0 is 0. What does that tell me? Not a damn thing. The test failed. I was hoping that would go to something other than 0. So, do I want to try and integrate that? Sine of 1 over n? Do I want to compare it to something? What in the world do I compare that to? Right? I mean, this is not obvious at all. Could we even integrate that? Let's just think about this. Could you even integrate sine of 1 over x dx? Could you even integrate that? I don't know. I don't think so. The only thing that comes to mind here is like integration by parts or something like that. Let's see, how long is my video? Damn it, I'm gonna have to cut this video real quick. When I cut it, I'll come back and finish this. I'm not gonna be able to get the last two onto this video, so I'll cut it here. I'll let you think about this. This is a good one. Let you think about it, and I'll come back.